Hello, my name is Jessica Page. I'm a PhD candidate at the University of Alabama, Huntsville, and I'm going to talk about Bayesian time delay interferometry for orbiting LISA. So the whole point of time delay interferometry, or TDI, is to suppress the overwhelming laser frequency noise, which are fluctuations of the laser frequency about some nominal frequency. The fluctuations are not automatically canceled during the taking of the interferometric measurements because the incoming laser light is delayed by the light travel time between the spacecraft of LISA. So the arms of the interferometer are never going to be equal. Laser frequency noise is by far the loudest source of noise at about 10 to the 7 times higher amplitude than the gravitational wave strain. So it needs to be suppressed, and you can see that example here. So what is time delay interferometry? Very briefly, it is the suppression method of the laser frequency noise. It works by linearly combining data streams shifted by the light travel time between the spacecraft to basically digitally represent an equal arm interferometer. To do this, you need to have prior knowledge of the spacecraft separations, and throughout this, I'll be using this terms arm lengths and delays, spacecraft separations, they all mean the same thing. Denoted by Li and Li prime here. And we need to know them to nanosecond accuracy. The XYZ channels that you'll see demonstrated later simulate an equal length Michelson interferometer at one of the spacecraft. So X is for spacecraft 1, Y, Z, and so on. The kind of framework for how it will work is it will be a pre-data processing step using pseudo-random noise phase modulation to obtain the values of the delays. Then you process the TDI channels and you give the laser frequency noise suppressed data to the signal analyst. However, a complementary method to this is time delay interferometric ranging, or TDIR, first proposed by Tinto et al. In 2005. And what it does is estimate the delay parameters needed for TDI with the raw data by minimizing the power of the residual laser frequency noise. So this is beneficial. It provides a backup method for laser frequency noise suppression, and it could reduce the amount of communication needed. And the actual light travel times that we need, as I mentioned, we need these nanosecond accuracy. They do this by using fractional delay interpolation, which we are also going to apply here in this work. Which basically is a convolution of the data with a windowed sync function. So here for this work, we are extending upon this idea to kind of do it in a Bayesian framework and estimate the delay time parameters using a Markov Chain Monte Carlo algorithm. So the motivation behind this is that we know that our astrophysical inferences are going to be made using a parameterized model of the LISA response function to gravitational waves, which includes the arm lengths themselves. So if we can incorporate TDIR as part of like an overall global LISA data model we can produce gravitational wave inferences that are marginalized over the uncertainty in the spacecraft separations that we can obtain by using these Bayesian methods. We also are naturally going to end up measuring the separations in time, which can lead to an independent reconstruction of the spacecraft orbits, which is kind of the focus of this leg of the project here that I'm talking about today. And then I'll briefly touch on the previous work in this overall project, which kind of laid the foundation for these goals by demonstrating an MCMC algorithm that estimated the arm lengths for the rigidly rotating spacecraft configuration. Here today, we're extending upon this and accounting for orbiting LISA. First, I'll touch on the previous work. When you're doing the fractional delay interpolation, you always have to cut off some of the data at the beginning and end of a segment after you've interpolated it. And the amount you have to cut off is dependent on the filter length used itself in the convolution. And so the shorter the filter length, the less data you have to cut off, and we want to cut off as little data as possible. The minimum filter length required for a given sampling rate depends on the interpolation error as a function of frequency. And it turns out that the maximum interpolation error happened to be always at the very highest frequencies of the LISA band at about 1 Hertz. But in our likelihood function of the MCMC, we actually cut off the frequencies summed over in the likelihood function at 0.1 Hertz for this previous work. So we tested whether we could lower the filter length and therefore lower the amount of data necessary to cut off, since we're already cutting the likelihood function off at 0.1 hertz. And it turns out we could. We ran this test over lower filter lengths than like the theoretical filter length n equals 49 for 4 hertz of data. And yeah, we found that we could get down to about 10 or n equals 23 before things start to look a little different in these distributions. But we decided to settle on n equals 29 because that's kind of the point where this trend in the chi-square part of the likelihood kind of stops, looking a little wonky. We kind of wanted to avoid this, stay on this asymptotic part of the filter length. So in the paper, we just said that n equals 29 is the safest bet. So at n equals 29 rather than n equals 49, that is a 40% reduction in data loss if you just estimate and assume a LISA duty cycle of 75%. So I haven't done this yet for the orbiting data, but this might be something that we can look at as well. Here's just the distributions from the previous work and some parameter summaries up here. So you can see we're estimating pretty good in the rigidly rotating case with laser frequency noise only, and when we include the secondary noises. Okay, so now we'll move on to orbiting LISA. So when accounting for LISA in orbit, the arm lengths not only differ in the direction of travel, like we accounted for in the previous work, but they also vary in time at about 1 meter per second. So once you account for the LISA in orbit, you need the second generation TDI channels, which have the delays that are non-commuting. And so the order of the delays applied in the prescribed TDI channel matters. You can't apply them out of order. So this is what this looks like. So if f of t is, for instance, an interferometric measurement, and we apply the delay operator on it, it's going to be that function delayed by the light travel time. And then if we have two delays prescribed in the TDI equation, you first apply the delay closest to the measurement, and then the second delay is going to, the first delay applied is going to get delayed by subsequent delays. So the data we used here, like I mentioned before, instead of independently simulating data for the study, figured it'd be better to use already publicly available software. So we use LISA instrument. And so the specifications for this are Keplerian orbits. We used right now just 1 hour of data because this is still in the early phases. And we're using an MCMC, so I'm trying to optimize on the computation time. So right now it's just 1 hour. The previous work had about a day. 4 hertz sampling rate, no anti-aliasing filter, just laser frequency noise only for now, but we will add the gravitational waves and the secondary noises later. So what I am going to do for these now non-commuting delays for an MCMC is use some approximations. So for an MCMC, we're estimating the parameters for these arm lengths. And even though they're a time series, we can't necessarily do that in the MCMC efficiently. So I've been looking at the approximations. People have already shown that that second generation TDI suppresses laser frequency noise to first order in the delays. So if we just approximate that delay application as a linear function, it looks like this. And then if we, for every new delay applied, when you're using the linear approximation, it looks something like this. So you have a constant value for the delay itself in there. These should actually be L dot right here, sorry. Yeah, going to generate a first order correction for every delay applied. I've also looked at using the quadratic approximation for longer chunks of data, because I'll show you in a moment that that might end up being necessary. So I found a way to use the quadratic approximation in my code, even though, however, the plan for the MCMC anyway is to estimate on chunks of data that the linear approximation is sufficient. So we will see, it's still in the early stages, but here's an example of the linear approximation of suppression of the delays versus the quadratic. So this is This has not gone through the MCMC yet. This is just using the truth values from the data simulation. For just 1 hour of data, both seem to work fine. The quadratic, works excellently if you compare it to the pi TDI suppression, which uses the full interpolation of the delays rather than using any approximations. And then the linear approximation is doing pretty well. But then when you get out to just 1 day of data, which is what I used in the previous work with the rigidly rotating case, it does not suppress quite as well, the linear approximation that is. And so there's a few things going on here. This curve, this kind of threshold curve, or the analytic form of the secondary noise curve has not been updated to LISA instrument secondary noise parameters. So that could have something to do with it. But as you can see, the quadratic approximation is doing much better for these longer stretches of data. So that might be useful in the future. The MCMC algorithm for for orbiting data is still under work. We don't have any posteriors to show yet, but it's probably going to look similar to previous work. So right now I just have a uniform prior for all the parameters. Now, since we're using the approximation, we have the L dot parameters. Li dot is equal to Li prime dot. So I only have 3 extra parameters now. The maximum likelihood has been increased to 0.5 instead of 0.1, which I had. The maximum frequency and the likelihood has been increased to 0.5 instead of 0.1 hertz, like I had in previous work. So it looks like we might still be able to do the filter length test that I showed before. And so far the likelihood function looks the same. It's just the XYZ channels have now been updated to be the 2nd generation XYZ channels. So yeah, MCMC is currently in progress. I'm working on ways of optimizing it and speeding it up to be able to handle longer stretches of data possibly, and just to be able to get estimates in a good amount of time, because with the previous work in the rigidly rotating case, I was able to make estimations in about 5 hours for about 50,000 samples on the MCMC for 1 day of data. So working on getting closer to that ballpark of computation time. And then eventually I will work on the overall goal of this project, which is to include the gravitational wave signals and measure the effects of arm length uncertainty in signal estimation. So that's what I have for now. Thank you for your attention.